Okay. So the next thing that we pick up is we're going to start doing, so far what we've done is we've done kinematics. And in our kinematics, the key here is we've gotten our toolkit without regard for the motion. Okay. We've done this without regard for motion. So we've got those equations of motion and we've gotten things that are there. But we know a couple of things. One, if I have a box here, and this box has mass, and I have another box, and we're going to use the representation of our masses to mean actually different. If I want to get this box moving, I have to do something. I have to push it. I have to pull it. I have to do something. So we talk about forces, and usually we talk about contact forces. And we usually say that these are going to be a push or a pull. Now we have other kinds of forces. If I have a ball and the earth here, if I have this ball and it's some height above the earth, and unless I'm holding it up and I drop it, I have to be doing something in order for this ball to stay there. I have to put a table between it. I have to do something else. I have to have this. And this is what we call a field force. And we have several field forces. We have gravity as a field force. Magnetism is a field force. And electric fields are a field force. And these are going to have a little bit of differences that are doing there. But gravity is something that we don't normally think of when we think of forces, because what we're trying to do is getting something to move. We get this back and forth. Now, the other thing about this is if gravity is pushing on this, something else is happening in the other direction. The ground is pushing back on it. So the mass is actually pushing on the tabletop. The mass is pushing on the earth. The mass is doing something, and we're getting a force back up. So we get some postulates. Newton gives us some postulates here. One is if I'm in space and my object is moving, we've got an object in motion, remains in motion, or an object at rest, remains at rest, unless acted upon by an unequal force. So if this is in space, this is going to go on in space, get going on forever and ever and ever until it hits a wall. This mass, if I don't apply a push or a pull here, it's going to sit on the tabletop until something comes along and bumps it. But we also know something else. So this is Newton's first law. And then we get Newton's third law. And Newton's third law says forces come in pairs. So my force that the mass is applying, the ground is applying an equal but opposite force. So even if I put a push on here, my mass is going to be resistant up to that until I can get a push that gets this moving. And mass, which we've defined as stuff, gives us this characteristic of this idea that an object's going to remain in motion unless something applies to it. This gives us that idea of inertia. The more mass there is, the more inertia there is. So I'm going to have to apply a bigger force to get this mass moving than I would over here, because there's more stuff here than there is over here. So force is directly proportional to mass. This gives us our idea of inertia. So we get that overall picture of inertia. We know this. We've been playing the gravity game for a long time. We've been playing the push-pull game for a long time. And we intuitively know that if I'm playing tug of war, right? I got my person over here and I got my person over here. And this person is applying a force in this direction. This person's applying a force in this direction. And I've got the flag there. If this person is applying a force in that direction and this person is applying twice the force in this direction, we know the flag is going to move in that direction. And we intuitively know that the flag is going to move in that direction based off of the sum, and that's what this means, the sum of my forces. So the sum of the forces here is I have force 1, and that's going in the negative direction, and I have force 2 going in the other direction, so I end up with a positive force over there. And the thing about these is forces are vectors. They have direction and magnitude. So several of you have that problem here. So we have the box problem. And the box is I'm applying a force upward of 10 newtons. And I'll show you that it's newtons here. But we've written my force vector this way. And then I've got somebody pulling this way. And the force on this one, we're going to say is 15 newtons. And we're going to give ourselves that this is 30 degrees. We have to convert this force into the force vector is 15 cosine 30 degrees in the I direction plus 15 sine 30 degrees in the J direction. So we now have my vector. This gives me 12.99 in the I direction. And 7.5 in the J direction. And we want to know how this block is going to move. So we're going to add our forces. So I'm going to do my force 1. I'm going to go ahead and write it as 10 newtons in the J direction. I'm going to do my force 2. And it's 12.99 in the I direction plus 7.5 in the J direction. My sum of my forces is 12.99 I plus 17.5 J. Then I can calculate the magnitude of my resultant force. That is the square root of 12.99 squared plus 17.5 squared. Under the square root, I've got 224.99. And this says 14.999 or approximately 15 newtons. That's the overall magnitude of the force. But the direction of the force is going to be the angle, which will be the arctangent of my 17.5 divided by my 12.99. And that says that that's going to be 53 degrees. 53.4 degrees. So my resultant force on this box is going to be somewhere right in through here. So this is just, this particular homework problem was just a force addition problem, but we could actually do this initial force addition problem. So we've been at this for a little while. I want to make sure you have time to do your labs because you've got 3 labs that are due this week. I also want to give you a little time to start looking at the forces before we dive in a little bit more. So I will stick around for questions and I will let you guys take off and get everything else done.
I have 2 questions, please.